Now, there also might be some of these may not be ones that we can explicitly solve for as a function. Put it in function notation, you know what I mean? In this case, we could say z equals that. But as we know, sometimes we have to implicitly define our our function, so we might have to do some implicit differentiation here. Let's see how that works. Let's say we've got xy plus z cubed x minus 2yz equals 0. Obviously that's going to be difficult to explicitly define z equals, we can't get an explicit z equals expression out of that because it's z cubed and z. However, we still might be interested in the tangent lines, slope of those tangent lines that we're talking about. So how do we get? And in this, I think in this case they use this different notation. How do we do the partial derivative of z with respect to x? Something like that. Well, we've got to use implicit differentiation. Now let me review that just real quick here. Let's say we've got y squared plus 3xy equals 6, and I want dy dx for that. That's our implicit. Remember that what we had to do is to get dy dx out of that, since we can't get y equals explicitly, we use this implicit differentiation. And remember the rule on that. What would, if we get dy dx out of this, what derivative do we get from y squared? Well, since we're doing the derivative with respect to y, derivative of y with respect to x, we've got y squared, which, power rule just tells me that's 2y, but since I'm wanting the derivative of y with respect to x, what else do I need? I need the dy dx, right? And then over here, I've got to do the product rule first times the derivative of the second. So it'd be 1, but it's a y, so I've got to do dy dx. Then I reverse that. The derivative of the 3x is just 3, since it's already an x. And then we solve that for dy dx, right? So we can factor it out of that. And of course, move that over. So, dy dx is make it 3y over 2y plus 3x. Okay. So it's a roundabout sort of way of getting our derivative respect of y with respect to x. Well, same thing we can utilize over here. If I'm wanting the partial derivative of z with respect to x, what have I got to do here? So over here, basically what I did is I ddx both sides. Well, if I partial derivative with respect to x over here, what happens? So I'm going to do the partial with respect to x of xy z cubed x. Well, that's telling me, of course, I'm doing it with respect to x, and I'm wanting the one partial derivative of z, so the y is the constant, right? And so what would this be when I do the partial derivative with respect to x? It would just be y, right? Y times 1. All right, so on this one, I've got to use a little product rule, right? Yeah, because I am wanting the partial of z with respect to x. And so this, what I'm essentially saying is this is something in terms of x and y. I'm just not getting it explicitly. So when I do the partial with respect to x, partial derivative with respect to x of this, that's going to be a little more complicated. Like I said, 3z squared. And since I don't know what z is in terms of x and y, I'm just going to have to say it's the partial. There's also the partial derivative of z with respect to x of that. But then I'm going to have to reverse that and do the product rule. So I do that times the derivative of x, which is 1. Okay. Now, I don't have quite the same difficulty here because the y is a constant, so it's just negative 2y times z. So I just have to do the derivative of the z, which is negative 2y times the derivative of the z, which is b1. But you need the partial z with respect to x. Just like on the other. Does that make sense?
It's funny because that character, that's delta, but it's lowercase delta, but it's been flipped around.
Yeah.
I don't know why.
And then just solve that for partial derivative of z with respect to x. What do we got? These two, so move the other two, or it might be easier to move these two, and I don't know. Either way. All right, so if we factor those off, 3z squared minus 2y, move those two over, so minus y minus z cubed. So the partial of z with respect to x is negative y minus z cubed over 3z squared minus 2y. Well, the problem there is you got z in your notation there, so it'd be a little difficult to find out what z is there. All right, so let's reverse that. What about the partial of z with respect to y? Well, same deal, but we do the partial with respect to y instead. And that changes things up just a little bit. This first part, now that we're doing with respect to y, derivative there would be what? Just x. And then here, x is just a fixed, so it's constant, so that would just be x times the partial of that. It would be 3z squared. And then we do need the partial derivative notation there for that, since we don't know what z is in terms of y is. All right? So far so good? And then minus, now we do have to do the product rule there, so y times the derivative of the z would just be partial of z with respect to y. And then reverse that, so that would be z times negative 2, right? Right side is just derivative of 0. Let's see, do we get something similar as we had before? So here's our two derivative terms, so factor that off, so we have 3xz squared minus 2y equals, move the other two terms over, so that would be positive 2z minus x. And so the partial of z with respect to y would be 2z minus x over 3x z squared minus 2y. Looks a little different, doesn't it? Sometimes you get some symmetry amongst your two there, but a little different. Okay? Not too bad, right? Okay, well, let's go back to our regular explicit function in z. All right, let's say we have where z equals, or f of xy equals x squared plus y squared. for that function in two variables. Let's find partial of f with respect to x at 1, 2, and then interpret that geometrically. As a slope. Well, it's not too hard to calculate that, is it? Partial derivative of f. Because the partial derivative of f with respect to x would just be 2x, and so partial derivative at 1, 2 would be what value? 2? Yeah, because we just plug in the x as 1, so we have to plug in the y. So the partial derivative of f with respect to x is 2. Well, that of course means a slope, but what slope are we talking about there is basically what we're looking at. And so let's see if we can graph this thing and draw the interpretation up also. What does that, any idea what that looks like? Cylinder? Well, obviously we're only going to be dealing in the top half, if you will, right? Because you're not going to get any negative values. Z is always going to be a positive, and of course we've got 0, 0. Now, if you think about slices here, or xz, the xz plane and then the yz plane. If we're just in the xz plane, we're looking at z equals x squared, which is a parabola opening up. Yeah. And then the same thing if we're only in the, we're talking about a parabola there. So yeah, we're looking at this paraboloid where you got kind of this rotated three-dimensional parabola. Okay. All right. Now, we're talking about at 1, 2. So x is 1, y is 2, and then the z, if we do that, would be 5, right? So at 1, 2, we're up here at 5. Should be somewhere like that. That's about right. Okay, right there. So we're on the outside of that paraboloid. 1, 2, 5. All right. But slope-wise, what are we talking about? Well, since our y is fixed, let's think about that. The y is fixed to be 2, right? And so we're talking about z equals x squared plus 2 squared. So that's z equals x squared plus 4. And if you think about that in the xz plane, we're talking about another parabola, right? Parabola shifted up 4. And we're in the y equals 2 plane. And so we're kind of slicing this up, but when we slice it up, we see what it looks like, a parabola. And so and it goes through that point, and so it's up, raised up from the y-axis, of course. Or anyway, maybe something like that. We slice it at the y equals 2 plane. And so this then is the slope off of that at that point. So we got a slope of 2 there. That tangent line, the slope of it is 2. So anyway, okay. All right.
So can you make equations for this?
Yeah. Remember, if you want the equation of that tangent line, you got the point, and you just need then the direction, the direction vector. Yeah, point in a direction. Yeah. Just get your vector off of that. All right. Now, what time we got? Okay. Well, if it works for 2 variables, why not 3? Why not 4? You can do the same thing for 3 variable functions. So let's say we've got a function that's in x, y, and z. X sine of y plus 3z. And so what would the partial with respect to x of that be? Same deal, right? X is the variable, the y and the z are constant, and so sine of that is just a constant. So it'd be 1 times the sine of x plus 3z. The partial with respect to y, z and x are constant, so it's just x times the derivative of this, which would be cosine of y plus 3z, a little chain rule. The outside is sine, so the derivative of cosine don't change the inside. But then you do the derivative of the inside, it would just be 1 plus 0, so yeah, x cosine of y plus z. And then the partial with respect to z would be same deal, right? Y and x are constant, so it'd be x times the derivative of that, so it'd be cosine of y plus 3z, but it is 3z inside, so the derivative of that would be 3. So 3x cosine of y plus 3z.